Okay, welcome back to the second part of today's lecture on benzenes and aromaticity. What we are going to continue with is looking at the criteria for aromaticity, and we're going to see there's a wide variety of structures that give us aromatic or anti-aromatic systems, okay? So let's talk about that. What's the difference between aromatic and anti-aromatic by moving on to identifying the concept of aromatic. With an aromatic system, you have a possibility of being in conjugation with everything and getting that resonance stability, or you have the possibility of not gaining that stability. And the difference is, in an aromatic compound, you have to follow those four rules of being cyclic, having a p orbital, being planar, but you have an odd number of electron pairs. For anti-aromatic compounds, or the opposite of an aromatic compound, we actually follow the first three rules the same, but we have that even number of electron pairs. So in our Huckel rule, instead of being 4n plus 2 for an aromatic compound, we just have 4n for anti-aromatic compounds, okay? So that means if n is 0, that's 0 electrons. If n is 1, that's 4 electrons. And then 4 times 2 is 8, so it's 4, 8, etc. Let's see, 10, no, not 10, 4, 8, 12. So we have an even number of pairs of electrons, and so that we will see the difference between them, and they have different stabilities, and aromatic compounds react a certain way, and anti-aromatic compounds react more like alkenes, okay? So let's look at things that are aromatic, you know, planar, cyclic, completely conjugated, and 4n plus 2 electrons. Let's look at things that are anti-aromatic. We follow all those rules, but it has an even number of pairs of electrons. And then things that just aren't aromatic at all, things that don't meet one or more of those requirements, okay? So let's look at the first three right here, and we call these, you know, any kind of ring with multiple double bonds in it. They're typically called annulenes, because annule means, you know, a ring, and then ene is for double bonds, right? So any monocyclic heterocarbon that has alternating single double bonds can be called the general term annulene. However, not all of them are aromatic, anti-aromatic, but some of them are even non-aromatic, okay? So let's move on to that and take a look at which ones we have here. Okay, so if we look at the first one here, one of the first rules is cyclic, right? And so, okay, cyclobutadiene, well, it's got cyclo in the name, so it's got to be a cyclic, right? So that's good. That follows rule number 1, okay? Every atom in the ring must have a p orbital, okay? So if we look at this, every atom has a double bond on it, and that means that every atom in that thing has a p orbital because they have double bonds to make that thing. Okay, is the molecule planar? I think yes, this molecule probably is planar because it's in a tight ring. You know, even if benzene's planar, this cyclobutadiene is probably planar. And does it have an odd number of electrons or an even number of electron pairs? Now, if we look here, we have one pair here and one pair here. That means we have 2 pairs, which means it's an even number, which means it's anti-aromatic. Okay, so it followed 3 of the rules, but it has an even number of electron pairs, which makes it anti-aromatic. Okay, and let's talk through that same logic for benzene. We expect it to be aromatic because that's what the whole chapter is named after. So let's double check to make sure it fits our rules. It's cyclic. Every atom has a p orbital on it because of each of these has a pi bond. Right here, it is planar because of its sp3 hybridized, and those are 120 degrees apart. And it has 1, 2, 3 pairs of electrons, or an odd number of pairs. It has a total of 6 electrons. Therefore, it is truly aromatic. Okay, so now let's look at the next one up here. This is 8 carbons here, and we have 4 double bonds. So let's look at this, okay? So let's see, it's in a ring, so we got that. It's got pi bond. It's got a p orbital on each of the carbons here because it has pi bonds on there. But it's not flat because of the trying to get these at 120-degree spacing, because these are sp2 hybridized carbons. It is not flat, okay? So it doesn't meet the flat rule, so it is not aromatic, and it's not anti-aromatic either because it doesn't meet the flat rule. Even though it has a set of 4 pairs of electrons, giving it an even number of pairs of electrons, it's not flat. Therefore, it's not aromatic and it's not anti-aromatic. It's non-aromatic, okay? So, do we have to have neutral species to do this? Well, no, we don't, okay? So let's talk about determining aromaticity for things that might have charge and see if we can follow our rules on this. So again, our rules are must be cyclic. And so if we look at cyclopentadiene right here, it's cyclic and it has lone pairs here and here. But this carbon right here has 2 hydrogens on it, okay? If this is sp3 hybridized, there is no available P, okay? So this is a non-aromatic compound, okay? Because it has a break in that conjugation. Not every atom in that ring has a p orbital. So we're breaking this rule number 2. It is planar for the most part, and it has an even number of electrons in its pi cloud. So technically it could be anti-aromatic if this was not sp3 hybridized, okay? So let's look at it by, okay, let's take away one of those hydrogens and generate a carbocation. Okay. When we do that, let's look at our system again. We have it cyclic. We now actually do have a p orbital on this carbon because we've taken that hydrogen away. Remember, carbocations are sp2 hybridized and have an empty p orbital, no electrons in there, okay? So we meet the planarity, we meet a p orbital rule, but now we only have 2 pairs of electrons. So that means this cyclopentadienyl cation is anti-aromatic. Okay? So it's anti-aromatic because it meets every rule, but it has an even number of pairs of electrons. Okay? So instead of being that cation, what if we put 2 electrons in that p orbital? Okay? And we make it an anion. So the cation here has 0 electrons in that orbital, 0 electrons. This one has 2. And they're both in that p orbital because it's still sp2 hybridized carbon, okay? So let's look at that. We have it planar, we have it cyclic, we have a p orbital on every atom, and now we have 1 pair, 2 pairs, 3 pairs of electrons. That's an odd number pair of electrons, which means this is an aromatic compound, and it's an aromatic anion, okay? So aromaticity does not have to be a neutral compound, it can be a charged compound. If the electrons are in a p orbital and you have the right number of electron pairs, okay? So let's look at that a little bit more and just kind of figure out why that's working for us, right? So if we redraw that cyclopentadiene with its 2 hydrogens on it, we see we break conjugation with our sp3 hybridized carbon, okay? We don't have that p orbital to share in the system. But by removing a hydrogen plus and leaving the 2 electrons that were making that sigma bond, if we remove that hydrogen plus, we can get it to be sp hybridized and have a p orbital. And those 2 electrons are left over in that p orbital and then can be delocalized around the entire ring, giving us our cyclopentadienyl anion. And our cyclopentadienyl anion now has 6 electrons, which fits our Hubble rule and means it's aromatic and can be drawn as an aromatic system. okay? So even though it's an anion, those electrons are in a p orbital, meaning it satisfies all 4 rules for aromaticity, okay? So the other thing we can do is that, well, if we have electrons in a system, we should be able to draw resonance structures, right? So let's go ahead and draw some resonance structures for this system and see where we can do it. Okay, so we have our basic ring here, and I'm going to put our electrons in a different color so we can kind of follow them around the ring here. So if we have these here, and let's see, we take these electrons, push them here, these electrons will push here, and these electrons will push up to here. That's going to give us our next structure. In fact, I'm going to draw all 5 of these because the carbons don't break. Remember, when we have resonance structures, the carbons don't break. So I'm just going to draw all 5 of these. Okay, and then we're going to look where the electrons have moved. This lone pair has come in and is making the new double bond here and the new double bond here, and that lone pair is now up on here. Okay, it cannot go over here and make a double bond, and it can't stay here and make a double bond because of that, so that lone pair is now in that position here. So our charge in this species is here, and then it moves to here, okay? So if we have these electrons move in here, and these electrons move here, and these electrons move here, all right, we're gonna have our lone pair end up here, we'll have a double bond here and a double bond here, and our anion is now moved to a new position. These are all valid resonance structures because all we're doing is moving electrons, okay? So if we, let's see, we move these electrons here, these electrons go here, and then these electrons come up here. That moves our charge to here, because that's where our lone pair ends up, and our double bonds are now there. And we can do that one more time. Let's see, the electrons are going to end up, no, these electrons are going to move in here, these are going to move here, and then these are going to come up here on this carbon, giving us our anion in this position here, okay? Do we see how these are all equivalent resonance structures? We're just moving that charge around from atom to carbon to carbon to carbon to carbon to carbon, meaning we have a nice true resonance structure. So that if we look at our resonance hybrid, remember our resonance hybrid is the equivalent of all of these together, we get the structure we see here. We get delocalized electrons with a negative charge shared amongst all 5 carbons. Okay, so I said when we first started that the first criteria is the molecule must be cyclic, but it doesn't have to be a single cycle, okay? We can spread our aromaticity out over multiple cycles. Let me show you that right here. So we use the exact same rules we use for monocyclics. However, we look for the number of electrons in each ring, okay? So we have to have that 6 electrons or those 3 electron pairs in each ring to have it fully aromatic across the system. So let's look at that, and we're going to start with this one right here. And we have 1 electron pair here, 1 electron pair here, 1 electron pair here. So this ring is aromatic. And then we have this same electron pair can be contributing to this ring because they can be in resonance with that ring as well. So we have 1 electron pair, 1 electron pair, 1 electron pair, giving us 6 electrons total. So this ring is also aromatic. Each ring satisfies the 4 rules of aromaticity. If each ring satisfies the 4 rules of aromaticity, the multi-ring system is also aromatic, okay? So if we looked at anthracene here, let's look at that. So we have 2 electrons here, 2 electrons here, 2 electrons here, 6 electrons, that ring's aromatic. 2 electrons, let me change colors here. 2 electrons here, 2 electrons here, 2 electrons here, 6 electrons, that ring's aromatic, okay? Oh, now it's gonna get hard. We got 2 electrons here, we got 2 electrons here. We have 1 electron there and 1 electron there from those 2 double bonds, giving us a total of 6 electrons. That ring is also aromatic, okay? Do you see how that only the 1/2 of the electrons from each of these double bonds is contributing? So 1 electron from each of those double bonds is contributing to give us our total of 6 electrons, okay? So let's use that same rule and look at this system here. This is called phenanthrene. So imagine you're just adding rings together. So this one's pretty easy because we have 6 electrons here. And this one's pretty easy because we have 6 electrons here. And then this one has a pair here, a pair here, a pair here. So it also has 6 electrons. So all 3 of these rings satisfy the rules for aromatic. Okay, and we can extend this again and again and again until we get up to something like this right here, this benzopyrene system here. Now, if we look at the benzopyrene, we have to start finding where the electrons are. For example, in this ring right here, we have the 2 electrons from the double bond, but then each of these double bonds can only donate 1 electron to give us a total of 6 electrons. Once we get to these multi-ring systems, it becomes harder and harder to find your 6 electrons. But if you look for them, thinking that a double bond that is terminating into your ring can share those electrons, then where do we go? There we go. That still allows for following the rules for multiple rings. Okay, does that make sense? Right there. Okay, so as long as you're counting for like you know, 6 is probably the most common for the set. As long as you're counting those 6 electrons in each of those rings that are planar, you will be able to satisfy your Huckel rules. Okay, so let's talk about why we know that these things are different is because they have different reactivity than just regular double bonds. And so our aromatic compounds tend to be very stable. We're not going to do addition reactions across there and lose the aromaticity. So most of the time what we see is we see a substitution reaction on that, okay? And so, for example, if a compound is not aromatic, but a reaction that produces an aromatic product, that actually makes it happen easier, okay? So let's think about what does that mean, okay? So what I'm gonna say here is that this hydrogen here, because it will allow it to become a more stable aromatic compound, makes it more acidic than if it was a different sp3 hybridized hydrogen, okay? So for example, if we were trying to pull off a hydrogen here on ethane, we have a pKa of above 60. Actually it's around 52. It's just around, around 60 here, to try to take off that hydrogen on an sp3 hybridized carbon, okay? So that's not a very acidic hydrogen. That's one of the worst acids we have in our organic chemistry, right? To form this anion here. However, the pKa of one of these hydrogens, that first hydrogen in a cyclopentadiene, is actually way down here, just about where water is. That's the pKa of water, is around 16. So the fact is that this is a much more acidic hydrogen. And it has everything to do with the idea of once it leaves as a proton, kicks those 2 electrons in to form that resonance structure, that 6-electron aromatic compound, it is more stable. Because it got that more stability, that proton is much more acidic, okay? So we're gonna see that happen in a couple different ways as we go forward here. And then once we form that anion, of course, we can delocalize it across the entire system. Okay, so I said before that it has to be atoms in a ring. It didn't have to be carbons, okay? And each of the atoms have to have a p orbital available to you. That lends us to the idea that we can have atoms other than carbon in our rings and still have aromatic compounds, okay? So if we have an atom other than carbon, that's what we call a heteroatom, or a atom different than carbon. So things like oxygen, nitrogen, and sulfur can also contribute to aromatic systems as long as it follows all 4 rules, okay? So if we look at this example here where we have pyridine, we've replaced one of the carbons and a hydrogen with a nitrogen and a lone pair, okay? So this lone pair right here does not contribute to the aromaticity, okay? If we look at the number of, we have a double bond here, a double bond here, and the double bond here. This double bond here is where the p orbital is overlapping with the p orbital on the carbon next to it, okay? So this nitrogen is sp2 hybridized, and this electron pair is actually in that sp2 hybrid orbital. However, the leftover p is allowing it to double bond with the carbon next to it, giving it a total of 6 electrons in the delocalized cloud. See, a lone pair here, a pair of electrons here, a pair of electrons here, and a pair of electrons here, 6 electrons. It meets all the rules. Available p orbital, cyclic, planar, and 6 electrons, okay? Can we do that in 5-membered rings? Yes, we can, okay? In the case of something like Parol, which is this one right here, what we have here, instead of the lone pair being in an sp2 hybridized orbital, the hydrogen is in the sp2 hybridized orbital, and the lone pair is in that leftover p orbital, okay? So just because there's a lone pair on a heteroatom, you have to decide whether it is part of the aromatic system in the p orbital or if it's in an sp2 hybridized orbital. In the case of pyridine, it's in an sp2 hybridized orbital, and the p has a single electron in it contributing to the system. In the case of Parol, that lone pair, that pair of electrons, is in that p orbital, which means now you have 1 pair, 2 pairs, and 3 pairs. You have a total of 6 electrons, and that hydrogen is bonded to your sp2 hybridized orbital. So Parol also satisfies all 4 rules of aromaticity. Okay. And that leads us to a wide variety of different possible heterocycles here. And we have to figure out which electrons are contributing to the aromaticity and which ones are not, okay? So in the example of pyridine, those lone pair is not contributing to the aromaticity. In Parol, those electrons are contributing to the aromaticity. In furan, 2 of them aren't, but 2 of them are. So in furan, 1 lone pair contributes to the aromatic ring. The other lone pair is sp2 hybridized. Same thing for thiophene. One of these is in your sp2 orbital, the other is in your p orbital here, okay? And just like when we have multi-ringed systems, we can have multiple rings with other atoms in them, so that we can have other aromatic heterocycles that can be 1, 2, or 3 rings long. For example, here, all we've done is replaced 1 carbon with a nitrogen, but it follows the rules and allows it to be a completely aromatic system. Again, a 5-membered, 6-membered ring, because each ring has 6 electrons, both of those rings are aromatic. In the case of imidazole, these electrons are not contributing to our aromaticity. The electrons with the double bond to nitrogen are. These electrons are contributing to the aromaticity. So we can find them, the ones that are contributing to the aromaticity, and identify them as whether they are contributing or aren't contributing. Okay. Now in purine right here, let's see, these aren't, these aren't, these aren't, but these are. So let me draw them in red. These contribute, and these contribute to the aromaticity. The other electrons don't. Okay, so you should be able to see now what the 4 rules for aromaticity are, how to find those electrons, and how to meet all 4 requirements to gain aromaticity in our aromatic compounds. Okay. Any questions on that right now? This brings us to the end of 14, part 2. Okay, I'm going to stop sharing while you guys ask questions, and I'm going to pull up our last section here that I think we're going to finish up today. That'll give us a lot of time to work on the next 7 sections that are all the reactions available to us there. Okay, So if there are no questions, I'd like to talk about the spectroscopy as it relates to benzene rings, and another way to help us identify that these things are not like isolated double bonds, and they show up differently in our NMR, IR, and Proton NMR. And also, because they're conjugated, we'll actually see them in the UV vis, just like we saw in the conjugated systems from the previous chapter. Okay, so if we just look at benzene, all we have is carbon-hydrogen bonds and carbon-carbon double bonds, okay? So when we think about the two zones that those would show up in, hydrogen-carbon-hydrogen bonds show up in above 3,000 wave numbers, up to 4,000 wave numbers. So that higher band, and if you want a good remembrance about IR, NMR, and Proton NMR, go ahead and go to my track site or Canvas site. There's a spectroscopy overview slide to help you remember what I'm talking about as far as the different zones for IR and the different upfield and downfield shifts for NMR. Okay, so go look for that if this is seeming a little confusing to you. Okay, so our heavy atom, light atom vibration zone is from 2,500 up to 4,000 wave numbers. And we see that bond in there above 3,000. It's a little bit higher than an alkane would be, but it's right up there in that 3,000 zone. And then of course we see our carbon-carbon double bond frequency between 1,500 and 2,500. Okay. In Proton NMR, because the aromatic ring is so electron rich, it's acting as an electronegative element, and that shifts the protons up above 6 ppm, above even where you would find a proton next to an alcohol. So because it's so electron rich, it shifted way downfield, it's de-shielded. And so we actually see that effect on a 1 carbon over. That benzylic hydrogen is also shifted slightly above where it would normally be in the 0.9 range, but these hydrogens here are shifted up because of the electron density found in the benzene ring, okay? Now in a carbon-carbon double, in our carbon-13 NMR, the sp2 hybridized carbons tend to be in the 90 to 100, 60 to 90 range. However, because they are conjugated and have that extra electron density, they're shifted further downfield into the 120 to the 150 ppm range. Okay, and because we have double bonds that are in conjugation with the others, we actually have a pretty decent absorption in the UV. Remember, our UV starts at about 180 nanometers and goes all the way through the visible, goes up into the visible here. So benzene is colorless, but it does start to absorb UV light. And in our mass spectrometry, benzylic groups tend to always generate a nice, strong peak at 91 because of this benzylic cation and the stability of it. However, it's a monosubstituted benzene. You typically get a fragment at 77, which is 6 carbons and 5 hydrogens. Okay, so if we want to look at the IR and look at some aromatic compounds, we'll see that the absorption for the aromatic hydrogens is actually fairly about mid. It's not really strong. It's not as strong as a carbonyl or anything like that, but we do see it show up right here above the 3,000 wave number mark. Notice the ones below here, those are the sp2, sp3 hybridized, hydrogens, and the ones above 3,000 tend to be the sp2 hybridized hydrogens here. And then we see nothing in this larger band until we get down to these fairly moderate peaks in the 1,500 range. And then of course we have some stuff in the fingerprint region right here. Now, by adding additional alkyl groups to the system, we get stronger absorptions in below the 3,000 mark, but we still have absorptions above the 3,000 mark, and those are the hydrogens on the benzene ring. And then of course, these are our carbon-carbon and our carbon-carbon double bond stretches right here. If we functionalize it and get it in conjugation right here, we'll start to see additional bands in our carbon-carbon bond and our carbon-carbon double bond structures. And of course, if we add an alcohol to our system here, we're going to get that big, wide hydrogen bonding peak up here in the 3000 range. And all the other peaks can be attributed to carbon-hydrogen or carbon-carbon stretches. Okay, so let's talk about proton NMR a little bit. Again, proton NMR, the hydrogen will show up in proton NMR, and it's shifted downfield to approximately between 6.5 and 8 ppm because of the electron bent ring. Now, the aromaticity here drives that up to that range. Notice just in our cyclooctatetrene, remember, it doesn't meet 2 of the requirements for aromaticity, therefore it's not aromatic, okay? Because it's not aromatic, it is just an sp2 conjugated hydrogen, and it's much further upfield. It's less than 6. So aromaticity will drive that electron density, that de-shielding of those protons, and bring it higher field. In fact, by adding additional electron donating or withdrawing groups here, you can even shift it higher. So in proton NMR in proton NMR, if we're just looking at the hydrogens on the benzene right here, we will get distinct patterns based on the substitution we have for it, okay? So for example, if we have just mono substitution on here, that makes us have 3 different signals. We have the ones that are ortho, or the next to the substitution. These are equivalent and will give a single signal and will split other non-equivalent hydrogens, okay? The next ones over, because they are less electronically attached to the substituent, will be our next band, and these 2 are equivalent to each other. However, they're not equivalent to the ones next to the substituent or opposite the substituent. So we'll see a unique pattern here where we'll have 2 protons, and 1 proton. And the amount that they're spread apart is based on how electron donating or withdrawing that would be. Now, if we have a symmetrically substituted system right here, where we have a di-substituted system here, we end up having these 2 protons be the same, and then these 2 protons being different. So we're only going to have 2 peaks in that ortho di-substituted system, okay? In a meta di-substituted system, where they're 1, 3 apart from each other, we now have the proton in the middle is different than the protons that are next to the substituent, and it's different from here. So we're going to end up getting a different pattern from these and a different splitting pattern from those systems. And then, of course, if we have the same substituent on 2 sides here, that's going to make these all adjacent and to the substituents, and that's going to bring us down to a single peak. So these are the 3 common patterns we'll see in proton NMR for mono and di-substituted systems. Notice if you symmetrically substitute things, then your NMR gets simpler and simpler. Okay. So the last thing I want to talk about is on carbon-13. And just like in the proton NMR, proximity to the substituent will change the signal. So we're going to see different patterns for ortho, meta, and para-substituted benzenes, but it's going to be similar in the fact that we have the carbons that are attached to it have 1 signal, the carbons adjacent have another signal, and then the remaining ones furthest away have another signal. So we'll only end up with 3 NMR signals for this one. In the meta substitution, we actually end up with 4 types. We have the ones that they're attached to, the ones that they're adjacent, the one that's in the middle, and then the one that's opposite here. So we have 4 signals in carbon NMR for a meta substituted system. And when we go down to the para-substituted, just like in the proton NMR where it got simpler, we now only have 2 types of signals in our carbon NMR, the one where it's attached, and then the 4 other carbons are equivalent in that system. So we'll see a different pattern for ortho, meta, or para substitution in our NMR. All right, questions on spectroscopy? Again, go back to the track site and get the review of different types. When we're talking about proton, we have to remember equivalent and splitting. So look for equivalent hydrogens and splitting. In carbon NMR, all we're looking for is equivalent carbons. All right, so we're right at 1:40, which is right on time, I think. And so what I'm gonna do is I'm gonna stop recording, and then I will answer questions until you stop recording.